Hi, my name is Matthias Böhm, and I'm a BMK Endowed Chair for Data Management at ExDRa. It's my pleasure to present the ExDRa project for exploratory data science on federated raw data. This joint effort by Siemens, DFKI, TU Graz, and TU Berlin. Now, in order to understand the challenge of exploratory data science on federated data, we need to look into two subcategories of challenges. First, exploratory data science typically deals with open-ended questions and underspecified objectives, where data scientists in an iterative manner acquire the necessary data, clean and enrich these data before eventually building predictive models and testing those. In contrast to traditional data warehouse environments, in exploratory data science, the business value is typically unknown, which leads to a very limited investment into a systematic data acquisition and cleaning. The second major challenge relates to data ownership and privacy concerns. Due to privacy restrictions and geo-distribution data ownership, often it is not possible to centrally consolidate data for data cleaning and building machine learning pipelines. To better understand this data ownership dilemma, consider the following thought experiment. We have a machine vendor A that sells a machine to a middle person. That middle person uses that machine to test customer equipment. Now, who owns the data? I can make an argument that any one of those stakeholders has vested interest of owning the data. Machine vendor wants to use it for predictive maintenance. The middle person wants to sell data-driven services to a wide range of different customers, and the customer doesn't want to reveal the equipment characteristics. For that reason, it's usually negotiated in bilateral contracts, and it's a binary decision to share or not to share. Now, recent work on federated learning adds an additional point in this design space by allowing us to learn central machine learning models without central data consolidation, by essentially adopting a traditional pyramidal architecture and sumo distribution strategies. So we have an initialized model, distribute that to mobile devices, and those mobile devices now act as workers, do, for example, a forward and backward pass through a neural network to compute gradients, and then via means of secure aggregation, either share those gradients or the local models for model averaging. We believe that the opportunities of federated learning are much, much broader, especially in an enterprise context where you typically have legal agreements and some coordination among the involved parties. Now, our goal is to enable entire machine learning pipelines over federated raw data. So this idea essentially combines federated learning, puts it into an enterprise context with legal agreements, and then leverages ideas from query processing over raw data in order to avoid unnecessary redundancy in working with those raw data sets if we have multiple tenants or an iterative process of a data scientist. So in a sense, this creates a more fine-grained spectrum of data ownership, which has the potential to even create new markets. Now, in such an enterprise federated learning context, we are working with multiple use cases for fertilizer and paper production. So fertilizer production centers around a grinding mill that grinds phosphorus rock to produce fertilizer. For paper production, you have quality measures such as the C strength and the Scott bond that can only be measured once the paper is really wound up at the end of the pipeline. So there's an interest in estimate and predicting the paper quality as early as possible. Now, both use cases share the characteristic that if you could build a central model over multiple federated production sites, that we could improve data and model quality, and with that, improve the related processes. Now, in such environments, we see multiple different forms of federated data, both row partitioned, where the features are the same, but different federated sites hold different observations, as well as column partitioned, where potentially along the supply chain, you have different different features that augment each other. And in the general case, it's really non-overlapping parts of a virtual matrix. Now, in this enterprise context, we have a spectrum of different privacy models. And the key property is that we want to ensure that shared data does not allow the reconstruction of those private raw data. And the enterprise context now allows us to use very practical means such as aggregates or aggregates with encrypted communication for cost-effective federated learning. Of course, there are also environments that have stronger security requirements, and in those environments we would also apply privacy-enhancing technologies such as homomorphic encryption, multi-party computation, and differential privacy. Now, in order to really support federated learning in such an environment, we built the ExDRa system infrastructure that is composed of multiple components. At the very top, we have the Siemens ML workbench that allows data scientists to configure data sources and, in the context of projects, then create pipelines, configure those pipelines, and use interactive plots for result visualizations. It also has a backend that in Docker containers then runs the individual pipeline steps. At the very bottom, we have multiple different data sources, including structured batch sources, as well as streaming data sources. In order to perform federated learning, we extended two larger system projects, Apache SystemDS for the actual federated machine learning part, and Nebula Stream, especially for streaming data acquisition, where Nebula Stream deploys a decentralized topology of a continuous query in order to execute pre-processing steps and consolidate data into a buffered file sync with certain retention periods that allow Apache SystemDS to read a really consistent snapshot of data. In addition to that, there's an ExperimentDB for general model management, a model store, as well as pipeline recommendations. Now, in the second part of this talk, I want to talk specifically about the federated learning backend of Apache SystemDS. So at script level, it starts with defining such a virtual matrix that logically holds metadata for where the individual federated sites are, so IP and ports, as well as which fraction of a matrix is covered by a particular federated site. And then the general system architecture is composed of a coordinator and multiple workers that act as servers and wait for requests sent by the coordinator. Now, the coordinator executes a linear algebra program, and whenever an operation touches the federated data as a metadata handler, it uses federated dedicated operations to dispatch sub-operations into the federated sites, compute their local data objects, and potentially transfer aggregates back to the coordinator for executing the overall machine learning algorithm. Now, in this context, initially we started implementing dedicated operations, but it quickly became not scalable enough, such that we generalized that model into a set of 6 meta-federated requests, such as put, that allows us to take a local object from the coordinator and transfer it to all the federated workers, gets for obtaining certain data objects, but then also executing instructions, so core kernels, and user-defined functions at the federated sites over the federated data. Now, this design allows for reusing local operations from a local single-node backend at the federated sites as well, and it's generic enough to even allow for federated hierarchies, where at the federated worker, we might have such a metadata object that points to a hierarchy of sub-organizations. Now, in general, we want to support now linear algebra programs as well as federated parameter servers directly over those federated data sets. For federated linear algebra operations, we essentially extended all the operations that are possible to execute over federated row or column partition data, and using those federated requests to actually perform those operations. So as an example, consider a matrix vector multiply where the matrix is a federated row partition matrix. So we now use put to broadcast this local vector to all the federated sites. They perform a local matrix vector multiply, yielding with R-band semantics essentially another row partition federated matrix. And once the vector goes out of scope, we can appropriately clean up the other data objects that are no longer required. Similarly, for vector matrix multiply, again, over row partition federated matrix, we do a sliced broadcast where every federated site only needs a certain subset of the vector multiplied from the left. We perform a vector matrix multiply at the federated sites. And now we take those aggregates and get them into the coordinator where we do a final aggregate over those partial aggregates. At ML algorithm level, we try very hard to stay independent of federated operations. So the compiler automatically compiles federated execution plans, which is important for reuse. So for example, here we can reuse existing scripts for k-means and other operations. And in this example, the matrix multiply for computing Euclidean distances, additional row operations, they perfectly map into federated operations over a row partitioned matrix. And eventually, those federated objects, they are consumed by a column sums and aligned federated matrix multiply that really aggregates over both dimensions and then shares those aggregates with the coordinator. In addition to federated linear algebra, we are also supporting federated pyramid observers that extends systemd local and distributed pyramid observer for a federated environment. The architecture is very similar to local federated pyramid, multi-threaded pyramid observer, where two control threads act as the local workers and dispatch the federated requests to those federated sites. In order to respect the boundaries of federated data, we specifically extended our data partitioning techniques to perform reshuffling for randomization just within the individual federated sites and to handle imbalance and skew by means of virtual replication and weighting. In addition to that, we also support data preparation over federated raw data. So first, machine learning-based data cleaning validation that can directly use the backend for federated linear algebra. In addition to that, we have dedicated support for federated feature transformations. So consider the example that we have raw data at two federated sites. This federated feature transformation would first compute the distinct items for the columns we want to recode and later one-hot encode, and the minimum and maximum ranges for binned columns, consolidate that at the coordinator, and then distribute this consolidated metadata to all the federated sites to yield a consistent encoding. Now, interestingly, compared to stateless machine learning systems, those workers act now as stateful workers that allow for adaptive data reorganization across multiple requests in a multi-tenant environment, but also across multiple different invocations from a single data science workflow. Now you might ask, is this deployed in practice yet? And the honest answer is no. We're using production use cases, but it's not deployed fully in production yet. However, our envisioned deployment looks as follows. You have those multiple different federated sites that might have a complex system architecture inside and typically have enough IT infrastructure and resources to actually allow for federated learning. So in such an environment, we would have the coordinator being on the laptop of a data scientist or in some central infrastructure, and then federated workers at the individual federated sites. Nebula Stream would then deploy a decentralized topology over multiple potentially unreliable and moving streaming data sources in order to consolidate data and hand it over via those buffered file syncs into systemd. Eventually, there's also a use case for private models where not the data stays private, but the models and the coordinator might share things to evaluate by those private assets of the individual federated sites. Now, to study the performance of the federated backend, we ran multiple different experiments in a cluster environment of 8 nodes and additional clients to test wide area networks. So the baselines are a local computation to see how much overhead does federated learning add, as well as a federated local area network setup, a wide area network setup where we ran the coordinator in Copenhagen, Denmark, and the actual federated sites in a 2-rack cluster in Graz, Austria, so a distance over 1,300 kilometers. And we also compare against scikit-learn and TensorFlow. So looking over a variety of different algorithms from traditional regression, classification, clustering, dimensionality reduction to parameter servers for mini-batch training, we see in a local environment a very small overhead. And due to the additional resources of multiple federated sites, even runtime improvements compared to local runtime. In a wide area network, we see substantially larger communication overhead, but it's still very reasonable and with that practical to actually deploy in practice. Now, how competitive is this local baseline? Compared to scikit-learn and TensorFlow, it is certainly in the same ballpark. The experimental results in detail are mixed. So there are cases where scikit-learn is 50% faster. There are cases where systemd is 2x faster, and similarly for TensorFlow. But this additional comparison allows us to extrapolate that via practical means of aggregates, it's indeed feasible to perform federated learning in such environments. Coming back to our paper production pipeline that now includes feature transformations and various pre-processing steps along with both batch and mini-batch training, we see that the federated runtime backend still allows us to compile plans that do not expose the actual raw data with very moderate overhead. So in summary, we presented the ExDRa system for exploratory data science and federated raw data that's through Apache systemd federated runtime backend provides federated linear algebra as well as federated parameter servers with very moderate overhead by relying on exchanging basic aggregates in such an enterprise federated learning environment. So in conclusion, federated learning is certainly applicable in practice, and the automatic generation of execution plans is crucial for automatically reusing existing libraries for data cleaning, pre-processing, machine learning, and training and debugging those models. Furthermore, this abstraction of federated data also nicely generalizes to multi-device settings. There's lots of future work, especially related to a deployment, which requires consideration of legal frameworks, business models, but also trusted system infrastructure, and being able to compile efficient execution plans in a federated environment under user-provided privacy constraints. And in order to avoid unnecessary redundancy, there's a rich opportunity for automatic compilation techniques, but also automatic data reorganization. With that, we believe that federated learning is very relevant in such an enterprise federated learning context and has the opportunity to create new markets. With that, thank you so much.